Good morning, my YouTube viewers. Crystal here. I just wanted to make another video for you. I hope the quality, the sound of this video is okay because I'm using my Chromebook and it seems to be picking up a lot of noise, even though I've got it set up so it'll only just accept my voice and not the computer noise. What I wanted to talk to you this morning about is I improved my score on the driven data competition for dengue fever problem statement, and I improved it about 1 point. The last time I did anything, it was 28 points, and then I did some feature engineering, and now it's 27 points, which is an improvement of 1 point. And since I improved it, I wanted to make a video on this. Although the best score was 10, so I still have a long way to go. But as long as I keep making videos and getting it on the leaderboard and moving up the leaderboard, that's what's important, is moving up the leaderboard. So because I've got a Chromebook, my Chromebook is not able to show my program on GitHub where I have my program stored. So I'm using NB Viewer. So if you are not able to do the notebook, then I would recommend you use NB Viewer. What I'll do is I will copy the URL. I'll copy the URL, and that way you can put it in NB Viewer if you want to. Or you can put in GitHub, whatever you want. So now what we are is we're actually in the program in NB Viewer. And we'll read the problem statement for this competition question. The problem statement is: dengue fever is a mosquito-borne disease that occurs in tropical and subtropical parts of the world. In mild cases, symptoms are similar to the flu, fever, rash, and muscle and joint pain. In severe cases, dengue fever can cause severe bleeding, low blood pressure, and even death. Because it is carried by mosquitoes, the transmission dynamics of dengue are related to climate variables such as temperature and precipitation. Although the relationship to climate is complex, a growing number of scientists argue that climate change is likely to produce distributional shifts that will have significant public health implications worldwide. In recent years, dengue fever has been spreading. Historically, the disease has been most prevalent in Southeast Asia and the Pacific Islands. These days, many of the nearly 500 million cases per year are occurring in Latin America. Using environmental data collected by various U.S. federal government agencies, from the Centers for Disease Control and Prevention to the National Oceanic and Atmospheric Administration in the U.S. Department of Commerce, can you predict the number of dengue fever cases reported each week in San Juan, Puerto Rico, and Iquitos, Peru? So that's your problem statement. So we have to predict the number of cases. In some ways, this seems to me like it's a time series problem, but the problem is that the times tend to overlap. And so since it seems to me to be a time series problem, since the times overlap, I'm not sure exactly how to deal with this. And the reason why is because I'm having to do everything myself. I'm having to learn it all myself. The only assistance that I'm getting is the internet. That's the only assistance that I'm getting, is I'm able to look things up on the internet. And I don't know what to do about a situation that appears to be a time series, but the times are overlapping. So as a result of that, I decided to use traditional machine learning methods. And we'll see what happens. So the first thing that we're going to do is we're going to load up our libraries, import them. I'll load the data sets now. The data sets are actually saved in my GitHub account. So you can use the data sets from my GitHub account if you want, or you can use the data sets from Data Driven. It's entirely up to you. But if you use the data sets from my GitHub account, you don't have to download the data sets. So that's positive. It's our train file. It's in a train file. The test file shows all the variables in the test file, except the test file doesn't have your target. Your train file has nothing in our train and our test. We have our labels, so your target is actually in the labels where it says total cases. It says city, year, week of year, total cases. Here's our sample. That's what Data Driven wants to see. Data Driven wants to see year, week of year, total cases. What to do is we have to merge the labels with the train. So train equals train.merge labels on city, year, week of year, how, left, and then we're going to look at the train file. And now we've got the labels, or we've got the target really on your train file. This is info on the train file, so you can see most of them are floats, some of them are objects. And so I decided to do a picture of the dengue fever. So we got case per city equals train, group by city, week, start date, total cases, sum, reset index plot. So the only thing that does is that gives you the total cases. It doesn't actually give you, it does give you the city, but it doesn't go backtrack, because I have one program where I used a different formula and it backtracked. It showed you where it was backtracking, where the times were going back, because what they did was they have like the first half of the data set is this one city, and then the second half of the data set is the other city, but the times overlap. And so because I wasn't sure how to deal with overlapping times, I decided I'd use traditional machine learning methods. I found out that you can use traditional machine learning methods on time series, which I didn't know that, but I do now. So what we did now is I just wanted to show the cases per city. So again, you've got the city, a week, start date, and total cases. So what we do is we check to see if we've got any null variables, null characters. And yes, we've got null characters that have to be imputed. So the first thing we do is we use the ordinal encoder, and we ordinal encode the city, and then we ordinal encode week, start date, because you have to do that because your city is a string and your week, start date is a string, so you have to ordinal encode them. Now, what I could have done is I could have broken up the week, start date into day, month, and year, but I decided not to do that. And the reason why I decided not to do that is because in this we already had year and week of year. So since we had year and week of year, I just thought, well, we're going to be duplicating effort if we have day, week, and year. So I just left it the way it was. And so what we've done now is we can replace all null values with median. And I found out something about iterative imputer, but I think iterative imputer deals with just numeric values, and I haven't used it yet. I think I tried to use it one time and I couldn't use it, but I think what you need to do is you need to take everything and you need to convert it down to a numeric value, and then once you converted it to a numeric value, then you can use iterative imputer. But I'll try to use iterative imputer at some point and see where we go. Let's just see here if we've got any. So if I wanted to I could have used iterative imputer. This one, I might go back and try to use iterative imputer and see what happens, see if my value improves anymore, see if my score improves anymore, because that's what you always want to do. You always want to improve your score. So I might do that, go through and use iterative imputer, see if my score improves. We have a graphical representation, so one city has more variables than the other city. We counted that. One city has 936 rows, and another city has 520 rows. And then we counted the total cases, and so you can see, 1 week there were as many as 350 cases, so that's not very good. Now what we do is we define our X, Y, and X test. And when we define our X, Y, and X test, Y equals train dot total cases dot values, X equals train drop week start date total cases, axis equals 1 values, X test equals test drop week start date, axis equals 1 values. So now we split our data set up for training and validation. X train, X val, Y train, Y val equals train test split. X, Y test size equals 0.1. Random state equals 1. Shuffle equals true. X train shape. And then we check the shape of all these columns, all these data frames that we created. Now we put the values on a standard scaler, and the thing to remember is that you only fit it on X train. So you fit it on X train, and you transform it on X train, X val, and X test. So now what we do is check the shape of X val, X train, X test. And now what we do is we define our model. We decided we're going to use ADA boost regressor and gradient boosting regressor. With ADA boost regressor and gradient boosting regressor, we've got 99.82. And we make our predictions on the validation set, and we had a 79.12, which is about a several point improvement over the last model that I did. And on our T-score, we got a 99, which I guess is pretty good. Now you check your YPRED. This is all the values in the YPRED. Created a data frame so you can compare the actual to the predicted values and see how well we fared. And now what we do is we predict on the test set. Final values equals model predict X test. Final labels equals final labels dot S type end, and then final labels. We put it in a data frame. We submit it, and we upload our submission. And when we uploaded our submission, we got about a 27, which was a 1-point improvement over the previous submission, which was 28. But the best submission is 10. So I still have a long way to go. But I just wanted to show you this program that I've written to show you that, yes, we can improve our score. So thank you very much for watching my video, and I look forward to making new videos for you. If you like the work I do and you want to make a donation, I've got my email address in the description link below. And the reason why is because I don't have enough subscribers, so I have to ask for donations if I want to make any money on this channel. Thank you.